Hi everyone, thank you so much for joining us today. Today we have a very special guest speaker session with us. Today we have with us Weijia Shi. I hope I pronounced it correctly.
Yes,
Uh,
right.
Weijia is a PhD student in computer science at University of Washington, advised by Professor Liu Zettelmoyer and Professor Noah A. Smith. She have been a visiting researcher at Meta AI working with Scott E. Prior to University of Washington, she graduated from UCLA with a BS in computer science and minor in maths. Today, she will be presenting her research on a new technique known as in-context pre-training, and the title of paper is In-Context Pre-Training, Language Modeling Beyond Document Boundaries. Thank you so much for taking out time, and over to you.
Yeah, thank you for the introduction. So, yeah, feel free to interrupt me at any point if anything is unclear. So I will get started. So today I'm excited to share my work on in-context pre-training language modeling beyond document boundaries. We study how to train language models to make them better understand contexts. So this is a joint work with my friends and colleagues at UW and Meta AI. And suppose we want to use language model to answer this question: who got the first Nobel Prize in physics? A standard approach called retrieval augmentation. First search, first search the web, like retrieve related web documents, and then these web documents, together with a query, are inputted into language models to generate the final answer. So in this example, given this question, who got the first Nobel Prize, we retrieved top 30 documents. And among the top 30 documents, there's one gold document. So document 2 here, it provides a gold answer to the question. So what the language model needs to do, it just read all these documents and the question and extract the right answer from the context. Do you think language model can do it? Yeah, we've seen like language model perform so well on way more like complex tasks, like passing the bar exam, like the college admission exams. So this task like should be fairly easy for language model. There's a recent paper called Lost in the Middle. Look into this. So they found when the Go documents is placed in the middle of long contexts, even though like our most powerful language models like ChatGPT, Claude, they have hard time to get the right information out. So this points to a serious problem. Like these language models are not that good at understanding information in the contexts. So these issues impacts not only just retrieval augmentation, but also a wide range of tasks that depends on the language model's ability of understanding context. So for example, in-house learning it's kind of new way for models to learn to perform new tasks. So instead of fine-tuning, language model read several label example that put in the context. Like here, in the input, we put several like sentiment analysis example with labels. And the language model read this demonstration example and learn to perform the new task like predict the sentiment of the test example. So how well language model perform using the in-house learning depends a lot on how good they can like extract information from the context. Yeah, another example is multi-document reasoning. The language model has to read several documents and synthesize and reason across them, and then piece together information to get the right answer. So this task also depends on the model's ability to understand context. So why do language model makes such mistakes, and how can we fix them? So we hypothesize this problem may come from the way we are pre-training these language models. Yeah, to better understand this, let's take a look at how current language models are pre-trained. So during the pre-training time, the objective is to predict the next token based on the prior input context. Let's say we have the input context for 2022, FIFA set the prize money at 42 million. Language models read this context and are pre-trained to predict the next tokens, like the highest so far. Suppose we want our language model to handle like 10,000 tokens during the inference. To make the language model able to read the 10,000 tokens, we have to train it on 10,000 token long input sequences. But most of the times, we don't have that many training documents which are that long. So the current pre-training method has to concatenate different random documents in the same input context. So like here, document 1 talks about Paris, but the document 2 talks about the World Cup. So, but if we trying to predict the higher so far, do we actually need the document 1 here? So the Paris document doesn't really help the language model to figure out something about like FIFA. But so since the documents are randomly concatenated, the prior documents provide no meaningful signal for predicting the next documents. So this might lead language models to start ignoring the broader context. So the concatenation of random documents happens a lot because we don't have that many long documents during pre-training. So let's take a look at Common Crawl, which is our like most common sources of pre-trained data. So on the x-axis, we got the length of the document, and the y-axis shows how many documents we have of each length. So we can see the majority of the documents are pretty short in Common Crawl, like less than 10,000 tokens. So in fact, only about 13% of Common Crawl documents contain more than 1,000 tokens. So this means when we are pre-training a language model with a context window length of 10,000 tokens, we often don't have a single long document to fill that space. So instead, we have to stitch together like random short documents to fill up the context window. So even though we can technically increase the length of the language model's context window pretty easily, this doesn't really mean the language model are getting better at reading and understanding this long input contexts. So how to address this problem? We propose enhanced pre-training. So the main idea is very straightforward. Instead of putting random documents together, we use retrieval to retrieve related documents and put them in the context. So for example here, so when the language model trying to figure out what comes next in the sentence, the higher so far, it can refer back to the previous documents that mentions like World Cup never awarded more than 10 million before 2022. And then the language model learn to infer that the higher so far. So by using this approach, we are basically teaching language models to read and reason across document boundaries. So here's a head-to-head comparison between the standard pre-training methods and our proposed in-context pre-training. Yes, to summarize, the standard pre-training methods concatenate a bunch of random documents, but the in-context pre-training place related documents together in the same context during the pre-training phase. So from our experiments, we find this small difference in how the documents are arranged during pre-training could make a really big impact on how well the language model understands this context. Do people have any questions? Okay, then I will talk about like how we how we implement the in-context pre-training. So here's the overview. In the first step, given the pool of pre-training documents, in-context pre-training methods starts by finding related documents among them. Like in this case, we have document 0 and document 9 are semantically similar to each other, and document 1 and document 3 are similar. And after finding these related documents at scale, the next step in in-context pre-training is to find a path that visits each pre-training document once, and at the same time, maximize the chance these related documents are visited sequentially. Yeah, so for example, like document 0 and document are related. So we want to find a path that can visit these documents sequentially. Oh, Lucy, have a question?
Yeah, sorry, really quick question. It was actually on the last slide and I just didn't jump in. So you basically had a slide comparing the standard and your proposed, the in-context pre-training. But are you going to provide metrics as far as the comparison itself? Or is that later on?
It is a very good question. So we did compute like how similar, like pairwise document similarity in that context. I use this like as a measure of how similar this like documents in the context. And we found we want this similarity to be high, but not super high. So if there are like duplicate documents in the same context, then the language model may just learn to copy from the prior documents. So we want it to be related, but not like duplicates.
Okay, thanks.
Yeah, I will explain how we make sure like the documents in the same context are not duplicates. So we have like, an additional like deduplication process to keep the diversity within the document and within the same context. Yeah, thanks for the question.
Of course.
Yeah, so yeah, after finding the related documents, we want to find a document path that can visit these documents and make sure the related documents are visited sequentially. So after finding the path, we concatenate all the documents along the path and split them into fixed size pre-training input contexts. So for example, we want to pre-train the language model with 8,000 context window. We concatenate all documents along the path and truncate it into like 8,000 long input context. So with this like a more coherent input context formed with the related documents, we pre-train the language model with the standard language modeling objective. So one key thing to point out here is that the in-context pre-training only change the document ordering during pre-training. So everything else in the language model pre-training pipeline stay the same. So this means that our method can be directly applied to any existing pre-training pipeline. So we see this as like big advantage of our method. Yeah, so this is a brief overview of in-house pre-training. Now let's dive deeper into the two steps in in-house pre-training, the finding related documents and the create input context. So for finding related documents at scale, to do it efficiently, we use a retrieval model paired with an efficient search index to link each document to its nearest neighbor documents. So let's say we have a document 5 here as our query document. We use a dense retriever to search for its k nearest neighbors based on the semantic similarity. So in our case, I might find like document 3 and document 7 are the closest to document 5. Yeah, to better visualize this document's relation in the pre-training corpus, we construct a document graph. So in this graph, each node represents a document. So whenever two documents are identified as nearest neighbor, we form an edge between them. So the weight of this edge in the graph is the cosine similarity between the documents. So by retrieving k nearest neighbor documents for each document in the pre-training corpus, we are able to construct our final document graph. Yeah, just to give you a sense of the speed of this step, in our experiments, we sorted like 235 million documents, which amounts to around like 300 billion tokens. So it took us around 6 hours over 32 GPUs to retrieve nearest neighbors for each document in the pre-trained corpus. So for experiments we did after the paper submission, we scaled this up to 1 trillion tokens, which is among around 700 million documents, and it takes roughly like 40 hours over 50 GPUs to finish this continuous neighbor search. Do people have questions about this part? Oh.
You also mentioned that you're keeping this document that are similar, but also not keeping the document that are too much similar. So is that done in this step, or do you pre-process that later on?
Yes, a good question. So we actually process it in next step. So because this step give us like the nearest neighbor documents for every query document. We also have a pairwise similarity score, and then we use this score to do the data deduplication to make sure the documents in the same context are not duplicates. Yeah, I will cover like in the this slide, like it's a benefit of a retrieval. We can do a semantic duplication. Yeah.
Got it. Thank you.
Yeah, so there's like a cool side benefit we get from this retrieval step. So it makes it easy to get rid of semantic duplicate documents, which are like document pairs are semantic similar, but not exactly identical. I think previous study called SemDedupe have shown that removing the semantic duplicates preserve the performance and speed up the learning. So when we retrieve continuous neighbor documents for each document in the pre-training corpus, we can easily identify these documents and filter them out. And this also helps us keep the diversity among the documents that put in the same context. Yeah, I've covered our first step, finding related documents. So next, I will talk about how we create info context from this like the document graph. Yeah, so the goal of the second step is to find a single path that visits each document once and maximize the chance that these related documents are visited sequentially. We frame this problem as a variation of the maximum traveling salesman problems, which aims to find a path that maximizes the total weight. So in our context, the weight refers to the document similarity. Yeah, let me work through a simple example to show how this works. So imagine we start with documents that hasn't been visited yet, like the document 0 here. In this case, we select document 0, and the next step you move to is unvisited neighboring document that has the highest similarity weight. So it hops over to document 9 and adds it to the path. So this process keeps rolling until we hit the documents where all its neighbors have already been seen. So like here, so assume document 9 doesn't have any unvisited neighbors left. Then at this point, we start from a new branch and repeat the previous procedure. So we extend the path with an add 0 to a random unvisited minimum degree document. Let's say document 1 here. Then we pick up from here and keep going with the same method. We move to its unvisited neighboring document, document 3, document 5, and document 7. So this algorithm will give us a document path that traverses the entire pre-training corpus. And the good side of this algorithm is it can preserve the original frequency of the documents. So each document are visited once when we build this document path. Do people have questions about this part? Okay, then yeah, I will talk about how we create input context from this path. So the next step is we simply concatenate all the documents along the path and split them into fixed size input context. So as I mentioned, in our experiments, we are pre-training language models with context window length of 8,000 tokens. So we take our big sequences of document paths and divide it into test chunks. So each chunk being like around 8,000 tokens long. And now I've gone through how the in-house pre-training works. Do people have any question about the method?
Yeah, I want to ask you, sorry, I want to ask you, but I'm not sure if it's better to ask you like at the end of the thing or not. Like, I was kind of curious about, I know you group the documents by semantic similarity, and that sort of like, it makes total sense to me and why it like performs better. But I was kind of curious also about you ordering the groups of these documents, if there is like some effect onto the model performance, because the groups at the start, at least my sort of hypothesis, like the groups that you propose at the start set the latent space for further groups down the line. So you will be training, but like you're seeding the original training like at the starting epochs using like the, or fine tuning if you're doing like you're using the specific theme or specific like content of these documents. They're all similar to each other. So in terms of like inside the group, there might be like high diversity, but like in terms of all other groups, the diversity might be low. So I'm kind of wondering if like that has an effect on like final performance.
Oh, that's a really good question. I think so like example here, so we within the same batch, it could be like different context windows, right? So we only make sure the documents within the same context are similar, but different contexts within the same batch, we still keep like diversity. So you will like help avoid like the catastrophic forgetting. So for example, if we only train the models on like sports topic at the beginning and they never show any sports topic towards the end, then the model may just forget and everything about sports. Yeah, so we keep the diversity within the same batch. Yeah, but we make sure the document within the same context are similar.
All right, thank you. Yeah,
Yeah, we find it's very important because at the beginning we didn't keep that diversity within the same batch. I found like the model doesn't, the learned model are not very good. Yeah, thanks for bringing this up. It's a very good question. Okay, so so next I will talk about our experiments. We pre-train language model to handle a context window length of 8,000 tokens. To understand how this method scales, we train 4 different sizes of language model, ranging from 0.3, 0.7, 1.5, and 7 billion. Today, I'm going to focus mostly on the results from the 7 billion models. Our pre-training corpus is made up of 300 billion tokens from the common core, which amounts to around 235 million documents. For the 7 billion models, we started from scratch and trained them on 128 A100 GPUs, and it took us around 9 days to get the training done. For comparison, we consider 2 baseline. So the standard pre-training methods, which places random documents in the input contexts, and the KM methods that places each document alongside its top key retrieve documents in the context. It's very similar to our method, but given the same number of training step, the KM methods exposes language model to a less diverse set of documents because documents can repeat. Like given a Cohere document, we put this like top K nearest neighbor document in the context, but it could be like repeated documents because like maybe one document is very popular, it could be the nearest neighbor to a lot of other documents. And to keep our comparison fair, we make sure all the models include the baseline methods and our in-house pre-training methods. The model trained using these methods are on the exact same corpus and have the same number of training steps. Yeah, recall that like I mentioned earlier that a bunch of tasks are impacted by language models' ability of understanding context. So does in-context pre-training improve them? Yeah, the answer is yes. We find for tasks that require language model to reason over context, in-context pre-training is much better than the standard pre-training method. And so we consider different tasks to evaluate the model performance, like retrieval augmentation, in-context learning, reading comprehension, is like knowledge conflicts. I will explain in more detail later, and long document reasoning. So we find there's some big improvements in the model performance when we pre-train language model using in-context pre-training. Yeah, let's start by looking at the first big benefit of our approach, in-context learning. So to evaluate the in-context learning ability of the model, we use 32 demonstration examples for each data set. We test this across different tasks like topic classification, sentiment analysis, NLI, and hate speech. And here's the results. So on the y-axis, we have the average accuracy across this data set. So the standard language model scored an accuracy around the 66. And then on the other hand, the model trained with the Cohere approach actually performed worse than the standard one. And this is likely because the Cohere method exposes language model to a less diverse set of documents. So it will learn less during the pre-training. And finally, we got the performance of our in-context pre-training model. So we call the ICLM here. It performs significantly better than the standard approach. So this means like the model trained with in-context pre-training is better at like learning new tasks from contexts. So another benefit is reading comprehension. So for evaluating this, we look at both single document reading comprehension task and the multi-document tasks. So here are the results. So the standard and KN perform relatively similarly, but the in-context pre-trained models, ICLM, significantly outperform the both baselines. And we saw an average improvement of 14% on the reading comprehension tasks. And the third benefit we observe is a retrieval augmentation. So here we look at two open domain QA data sets, NQ and TQA. So we consider two evaluation settings with retrieval augmentation and without retrieval augmentation. So with retrieval augmentation is like the example I show in the beginning. Like given the question, we retrieve top 10 documents from Wikipedia as an additional context to the question. So consistent with our previous finding, so in-house pre-trained models perform much better than both the standard method and KN method. And we also consider another evaluation that without retrieval augmentation. So this means the input is only the question. We don't retrieve any additional documents. So this tests language model's ability to use knowledge encoded in the parameters. And in this non-retrieval augmentation setting, we found like the in-house pre-trained models perform slightly worse than the standard models. So this means the models memorize less during pre-training, as like the prior documents usually like provide the useful information for the language model. So the language model doesn't really rely too much on its like parametric knowledge to predict the answer. And the next benefit is the long context reasoning. We consider 6 data sets from Scroll, and like we find our model is still better than all the baselines. Yeah. So the fifth benefit is knowledge conflicts. So this is a bit like a synthetic setting, but it shows how language models read context when context contain the information conflicting with the knowledge language model learned during pre-training. So for example, here we have the question, who the U.S. fought in World War I, and we have substitute context that provides like the fake information, like it swaps the right entity with Taiwan, and we see whether the language model can read this context and generate the right answer. And another benchmark we consider is called memo trap. The instruction is to write, for example, like write a quote that ends in the word questioned, and we have this like prefix of the quote, like what everyone say must be. And if the language model follows the instruction, then it should output question. But because like because there's a common like proverb, like what everyone says must be true, the language model doesn't follow the context, we just output true. So this task evaluate how language model read the context. And we find like our in-house pre-trained models is much better than baselines on this task, like require the model to read the context that may contain conflicting information than the parametric knowledge. Yeah, to wrap up our findings, so on tasks like retrieval augmentation, in-house learning, reading comprehension, knowledge conflicts, and long document reasoning, we've seen like in-house pre-training is much better than the standard pre-training methods. And yeah, before I move to analysis, do people have any questions? Okay, then next I will talk about the analysis. So during our pre-training process, we monitor on both the training loss and how well the model did on downstream tasks. So here's a plot showing how the training loss changed over the training tokens. So the training so the red curve is the in-house pre-trained model's loss, and the green curve is a standard pre-trained model loss. So we can see the training loss for in-house pre-trained models consistently remain lower than that of the standard language models. So the reason why the in-house pre-trained language models have lower loss, so we think because when predicting the next token, the in-house language model benefit more from reading a richer set of relevant prior documents, while the language model has limited information to rely on, so leading to a higher loss. And on downstream tasks, like such as reading comprehension and retrieval augmentation, we find after training the models on around 115 billion tokens, the in-house pre-trained language model is consistently better than the standard model on these tasks. And the performance gap remain consistent throughout the remainder of the pre-training phase. Yeah, and the next, we are curious how model performance scales with number of demonstration example in in-house learning. And so we find like the in-house pre-trained models maintain consistent performance gain over the standard methods as the number of demonstration example grows. Yeah, to wrap up the presentation, I'd like to share two quality examples from the memo trap data sets. So the first one is we want the model to write a quote that ends in the word frequent. And the standard models will predict dangerous, while in-house pre-trained language models predict frequent. Yeah, so the in-house pre-trained models follow the instruction better compared with the standard models. Yeah. And thank you for listening. And please let me know if you have any questions.
Yeah, thank you so much for your talk. This is fantastic. I had like a couple of questions, if you don't mind. One, I was sort of trying to think, given like recent news about like models that can hold about 10 million tokens of like context in that range, like really long context model, do you think like RAG, I mean, I know there's been a lot of discussion if RAG still makes sense. So I was wondering, like, what do you think as a person who like wrote this paper and like how you like implemented this chunking using RAG? Like, do you think what do you think about long context, like extremely long context model, and if your sort of pre-training makes sense for them, and how would it make sense for them, etc., etc.?
Yeah, that's a very good question. So I think the one benefit of retrieval, like I showed in the paper, is it can help group related documents in the context. So if we want to train the language model that can handle, for example, like 1 million tokens, then it'd be really hard to find like such long documents in the pre-training corpus. So I guess like this retrieval method can help the group related documents and connect them together and to build long context. And the language model can really learn how to reason across different documents. Because if we just have like 1 million long context, but random documents in the context, the model doesn't really need to refer back to the beginning of the context. You think it'd be hard for the language model to learn. Like
and within, yeah, sorry, and within this context, like when you're organizing these like related documents to feed into the model, whether it's like during training or during test, I'm assuming you're organizing them like in a way that's like most similar to least similar.
Yeah, it's most similar to least similar.
Yeah, so most similar to least similar. I'm kind of curious, like, so I know like the point is to stitch the documents that are most similar together. But I'm kind of curious, like, would it make any sense if you, for example, like when you had this, because like you're still stitching the chunks that are unrelated on its edges. So I was wondering if it would be better if it's more like, if the documents like stitched more like a normal distribution, like at the center, it's the most similar, and then least similar ones that go out, and then you match the chunks basically by edges to see like how the chunk of like one document, like let's say like you have an array, like on one side you're going to have like something that like has similarity with the other chunk, then you have similarity with another chunk like from the other side, and you like order them in a position like when you're training, like so that like basically the edges are similar too, but the middle within is preserved like within the chunk itself. So the most similar would be like in a way in the center. Yeah.
This is a very, very good point. Yeah, so in our it's probably we haven't studied this, but I'm currently doing the kind of continued pre-train setting, because like study this in pre-training is too expensive. So now I'm study this like how to arrange documents within the same context in the continued pre-training setting. And as you mentioned, like I don't think like putting the most similar documents together and then to this similar is a most effective way. So now I'm trying like to see how to arrange these documents based on like different like similarity, and then to make it like better context. I think you raise a very good point. Yeah, I think because like if we have like most similar documents together, then maybe the model just refer back to the like prior one. Then you will not like look at longer, even longer contexts. Yeah, thank you for bringing this up.
Yeah, that makes sense. I just have a last question. Like, I work, my research mostly lies within multimodal models. And right now, especially in like embodied AI and robotics, a lot of people are investigating VLMs. So instead of LLMs. And I was sort of wondering, like, do you think this kind of thing would be applicable to visual language models too? Because you also have to take into account some semantic meaning of images. Like, but do you think this thing would work for VLMs as well?
Yeah, I think like in VLM pre-training, there are not many like interleave documents. So for example, people use like image caption pair, but they're not like interleave image texts. Or like people use like the multi-model C4 and the obelisks. But I think those corpus, the image may not be that related to the texts. So I guess this could be the pre-train method could be an effective way to create like the interleave context for VLM as well. Yeah, so I'm also thinking about this. I think it'd be very interesting to explore how good like this method can work for VLM as well.
Thank you so much.
Thank you. And do people have any other questions?
I have a thought. I have a question that when we are pre-training while keep maintaining the orders of the document that are semantically similar, I wonder, like, when like for rag or for other stuff, I think there have been some papers that have shown that if the correct answer is in the top of the context or is at the very end of the context, then the rag system would perform better as compared to if it is in the middle. So I wonder if we are ordering the document similarly, how would that affect like this kind of ordering?
Oh, so you mean how the in-context pre-trained models perform in the retrieval augmentation setting? But in the retrieval augmentation setting, like maybe not the top documents have the right answer, but
Yeah, yeah.
I see. Yeah, we haven't looked deeply into this. Yeah, so but I guess it'd be more interesting to explore like how well the like how different the model behavior like is like compared with like the standard models. Yeah, I see. I'm also very curious about this question. I will look into this.
Right. Thank you.
Yeah, it's a good question.
Yeah, I think we can end the session if you don't have any other question. Thank you so much, everyone, for joining. Thank you so much, Weijia, for the session. Really enjoyed it.
Yeah, thank you for inviting me.
Take care, everyone. Bye.